Hello and welcome back. This is Jonathan Gardner covering Sergey Lang's Basic Mathematics. So this is section 13.2, polynomial functions. We've covered theorem 1 in the previous video, and to recall for theorem 1, we kind of need this result for theorem 2. So theorem 1 said that f of x is a polynomial with degree less than or equal to n. And so basically it's going to be equal to a0 plus a1 of x plus dot 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 all the way up to a in x to the n. And we found that if c is a root of f, then f of x can be rewritten as x minus c times g of x, where g is equal to b1 dot 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 up to b1 plus b2 x plus dot 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 up to b n x to the n minus 1. And we also found, kind of as a side note, that b n is equal to a n. So that last term has the same coefficient in both of these. Note that we start at b1, not at b0. Okay, so that was the results of theorem 1. Theorem 2, we're going to build on that result, and we're going to prove that there is a limit to the number of roots that a polynomial can have. Okay, so theorem 2 says let f be a polynomial with degree less than or equal to n, okay? And we have a n in that polynomial is not equal to 0, so that last term is not 0, okay? And then we say f has at most n roots, okay? And the proof is a little bit strange, but it's good, okay? So the proof is we are going to let c1 dot 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 all the way up to cr be roots. Okay? And we're going to say that r could be greater than or equal to n. Okay? So we know that we can rewrite f of x. We're going to rewrite it this way. F of x is equal to x minus c1 times g1 of x. So g1 is the first of these second functions that we introduce. Okay? Now, we know that c1 is a root of x, but also c2 is a root. So if we have c2, we pass in c2, then that's going to be 0. And that's going to equal x minus c1 times g1 times c2. Now, if it's 0, that means, I'm sorry, this is c2 minus c1. So c2 minus c1 has to be 0, or g1 of c2 has to be equal to 0. Well, these two numbers are distinct. They're different. So this is not 0. So g1 of c2 must be 0. So g1 has a root of c2. And so we can rewrite g1 of x to be the same as x minus c2 times g2 of x. Okay? And we can do the same reasoning for c3, c4, c5, and so on. So we can rewrite f of x to be equal to x minus c1, x minus c2, x minus c3, multiplying that all out up to x minus cn times gn of x. Okay? So we're just substituting these g1 functions. So we're replacing g1 with x minus c2, g2. And then we do that for g3, g4, g5, all the way up to gn. Now what is gn of x? Well, gn of x is going to be, start with some thing, right? That is the a-nth term of f of x because of this notation here. Okay, so that means that this is equal to, f of x is equal to x minus c1 dot 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 times all those x minus cn times a of n. Okay, and a of n is not 0. So this is all the roots that we can possibly pull out. Okay, so at most, r must be equal to n. Okay, so we can only have n roots of a polynomial function that's degree less than or equal to n, where the last term is not 0. Okay, that's a fairly involved proof. It might take some thought to think about this. You might have to work it out for yourself a little bit. There's a corollary here. Okay, and the corollary says, let's suppose that we could rewrite f in two ways. So we can say f of x is a0 plus a1x plus a2x squared plus dot 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 all the way up to a n x to the n. Okay, we could also rewrite this with a different set of coefficients. okay? And we're wondering, is f of x expressible with a different set of coefficients? Or do we always have to use the same coefficients for the same function? And so this corollary says that there is only one distinct way to write this. That if you're going to do this, then a0 has to equal b0, a1 has to equal b1, and in fact, ai has to equal bi for all I, and 0 all the way up to n. Okay, so all of these have to be the same coefficients. There's no other way to write this, okay? And the proof is a little bit proof by contradiction. So what we're going to say is, suppose that we had 0 function, which is f minus f, right? So that would be a0 plus a1x plus a2x squared plus an(x to the n). And we're subtracting b0 plus b1x plus b2x squared plus dot, 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 up to bn x to the n. So we can rewrite that as a0 minus b0 plus a1 minus b1x plus a2 minus b2x squared plus dot, 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 plus an minus bn to the x to the n, okay, times x to the nth power, okay? And then we can rewrite di is just going to be ai minus bi. So this is the coefficients for each of those terms, okay? Suppose that some of these di were not 0. So we take the largest di. So we're going to say m is the largest I such that di is not equal to 0. And then we can rewrite the 0 function as dm x to the m plus d to the m minus 1, x to the m minus 1, all the way up to d0, okay? Now, this guy has to be non-zero. The rest could be 0. Now, note that this is 0 for all values of x, so it has infinite roots. However, according to theorem 2, this should only have, at most, m roots. Okay, so theorem 2 says you can't have any more than m roots. And the fact that it's a 0 function says you have, in fact, infinite roots. And so this is a contradiction. And so if you were to assume that any di was not 0, okay, then we would violate theorem 2, and so it's not possible. So that's the corollary there. So we have, in fact, only one way to represent any polynomial with a unique set of coefficients. Okay, now a little bit of terminology here before we move on to the next section. So we're going to call the coefficients, these are basically a1 all the way up to an. These are the ones that multiply by some x to the power of, okay? Oh, I'm sorry, a0, we start with 0, okay? And then the a0 term is going to be called the constant term. So the constant term and all of the other coefficients, we call those the coefficients. Okay, so suppose we had the polynomial, let's use a different color here. We have f of x is equal to 4x to the 5th minus 7x cubed plus x minus 20, okay? So the coefficients here is going to be 4, 0, 7, 0, 1, and negative 20, okay? And the constant term is this negative 20 term, okay? Now, we're going to define what degree means now, okay? We're going to say that when you have f of x is equal to a0 plus a1 of x plus a2x squared plus all the way up to an x to the n, and an is not equal to 0, then f of x has degree, the function f has a degree of n. So n is the highest term that is not 0. That's the degree of the polynomial, okay? There is the 0 polynomial, which has degree 0. This is defined to be 0 for all values. So the 0th term in the 0 polynomial is in fact 0, and so it has degree 0. That is the 0 polynomial, okay? Note that in chapter 4, we solved for all degree 2 polynomials using the quadratic formula. Okay, for degrees 3 and 4, so these are equations that have x cubed and x to the 4th terms that have coefficients that are not 0. but no higher terms, no higher degrees, right? These are much more difficult to solve, and I'm not actually going to solve them as part of this section, okay? And if you get to 5 and beyond, and then that becomes ridiculously difficult to solve, and there is not a general result for degrees 5 and beyond that we have yet. So if you're able to come up with one, more power to you. Congratulations, you're awesome. Okay. Note also that typically in algebra texts, we talk a lot about the roots that are real or the roots that are integer values. And in reality, these are not very interesting. And there's a variety of techniques they develop that are basically useless for higher mathematics. So Sergey Lang here recommends not examining and not diving into how to factor and find the roots of degrees 3 and 4. It's kind of a pointless exercise. In general, when I've seen like standardized testing like the SAT and stuff like that, they use problems where it's fairly easy to visually identify the zeros of degree 3 and degree 4 polynomials. In the cases where they haven't, they generally give you one of the polynomials, and in which case, like if you have an f of x which is degree 4 and they say that it has roots c1 and c2, then you can just rewrite this as x minus c1 times x minus c2 times some other polynomial that will have degree 2. Okay, and that's typically what you can do on the standardized tests when you run into those problems. If you need to, which typically you don't. They don't actually get that deep into this area usually. So we have an example of how to factorize a polynomial. Let me grab a new piece of paper here. So the example, he says let f of x is equal to 3x squared plus minus 5x plus 1. Okay, and so in order to find the roots here, what he's going to do is he's going to note that we have the solution x is equal to minus b, so that's 5 plus or minus the square root of b squared, which is 25 minus 4ac minus 12, all over 2a, all over 6. So we have 5 plus or minus the square root of 13 over 6. And so we can rewrite f of x as equal to, he has a 3 times x minus 5 plus the square root of 13 over 6, and then times x plus 5 square root of 13 over 6. 5 plus the square root of 13 over x. No, minus. This is a 5 minus square root of 13 over x. Okay, over 6. Sorry, I'm getting so confused here. How did he come up with this? Well, he says that it has roots here. So we have the x minus one of the roots, x plus the other roots. And then we note that the nth term, the last term there in that g of x is always going to be the same as the highest term there. And so this is how you can factorize that quickly. That's theorem 1 and theorem 2. Theorem 1 basically that gives you all that. Okay, another example. He says, what if we have f of x in general is ax squared plus bx plus c. Okay, and in this case, the answer is rather easy to find. So if we have what is it? B squared minus 4ac is greater than 0. B squared minus 4ac is greater than 0. Then we know that there are two roots. Okay, and if we have b squared minus 4ac is equal to 0, then there's one root. Okay, and that's very straightforward. So if we have two roots, then we rewrite this as a times x minus c1 and x minus c2, where those are the two roots of the function, just using the quadratic formula to find them. Okay. There is another example here. He says, what if we had f equals x to the n minus 1? So f of x is equal to x to the n minus 1. And he says that we know that 1 is a root. Why do we know that? Because 1 to the nth power minus 1 is in fact 0. So we can rewrite f of x is equal to x minus 1 times something. Right? What that thing is, he doesn't give it here. But you can look at exercise 2 of chapter 1, section 6, and also exercise 6 of this chapter will tell you how to do that. Okay. And one little final note, and this is kind of more of an annoyance than anything else. So a little bit of a backstory. I was helping my niece, I think it was. She was in Korea and she was having a hard time doing her algebra. And I looked at the algebra she was doing. I'm like, why in the world are they doing this? This makes no sense. But basically you'll see long division. Okay, it's called the Euclidean algorithm for factorizing whatever. It doesn't actually factorize the polynomials. It allows you to find, anyway, it allows you to rewrite polynomials in new ways. Recall from elementary school. So we want to take 327 and we want to divide that by 17. So what do? Well, we write a 17 here, we draw this funny symbol here, and then we put 327 on top. And then 17 goes into 32 once. We take a 17, 1 times 17 is 17, minus that we get 15 left over, and 15 is less than 17, so we can continue. So we bring down the 7. 17 goes into 157. Well, we figure that out to be 9. So 9 times 17 is going to be 153. Okay, and then we have 157 minus 153 gives us 4. So we have 19, remainder 4. And so we can rewrite 327 as being 19 times 17 plus 4. Okay, so we basically said that when we divide by 17 into 327, we can do that 19 times and we have 4 left over. Okay. Now we can do this with our polynomials as well. Okay. But to summarize, for integers, we have some integer n is always going to be equal to some integer q times some integer d plus some integer r. Okay, for all integers. Okay, and q is greater than or equal to 0. R is greater than 0. R is greater than or equal to 0, and less than d. Can't be d, right? And this is what we have for a general long division proof. Let's do this for the Euclidean algorithm. So Euclidean algorithm if I can spell, says that any function f of x that's a polynomial of degree r, of degree n, there is, you can rewrite this as some q of x times g of x. He uses, I was going to use d for the divisor, and then you have the remainder of x. Okay, and it actually gives you, there are polynomials q, r, so the degree of r is going to be less than the degree of g. Okay, also we can, f must be f and g must be non-zero. Okay, how do we do this? Well, let's do an example. Okay, so we're going to say f is defined to be 4x cubed minus 3x squared plus x plus 2, and g will define to be x squared plus 1. Okay, so we're going to find q of x and r of x. Okay, so we'll put our x squared plus 1 over here. We'll draw that funny line there. We'll have 4x cubed minus 3x squared plus x plus 2. Okay, and the first thing we're going to do is we're going to say, so this x squared plus 1, in order to get that 4x cubed term, we need to put 4x here. So 4x times 4x squared plus 1 gives us 4x cubed plus 4x. Okay, let's put this actually over here. So line up the x terms. And we're subtracting, so we're going to get 0. We're going to get minus 3x squared. And x minus 4x is going to be minus 3x. We're going to bring down the 2 as well. Okay, so now we have the minus 3x squared term, so we say minus 3. So it's going to give us minus 3x squared. And then this is a plus. Minus 3 times plus 1 is going to be minus 3. And we're subtracting this, so this is going to be 0. Keep the minus 3x. 2 minus minus 3 is going to be 5. Okay, so we get q is equal to 4x minus 3, and r is equal to minus 3x plus 5. Okay, so we can rewrite f of x out to be x squared plus 1 times 4x minus 3, and then plus minus 3x plus 5. Okay, so there is our g, our q, and our r. Okay, that's what you do. I honestly don't really find a use for this. I've never really used this except for algebra tests, and I don't really see the point to proving this in the general case. I don't see the point in examining it very much, but it's there if you need it. If you do find a use for this, or if you're living in some country where this is on the standardized test, let me know what else you want to know about this so I can help you solve whatever problems you have doing it. Exercises are rather straightforward. There is a long section in the exercises about rational functions, okay, about what happens when you take a function and divide it by another function and they're both polynomials. That is very interesting. Okay, I encourage you to take your time with the exercises, especially that rational section. Learn what you can from it, and if you have questions, please ask in the comments below. Guys, have a great day. Take care, and bye-bye. Thank you for watching this video on Sergey Lang's Basic Mathematics. You can find the series on the left, and on the right you can click to support my channel. Thank you very much. Bye-bye.